All right, so thank you for the introduction. I'm more than happy to be here. I've been working right next door for about 6 years now, and I've always wanted to come in and network with you all, and I'm glad I finally got the chance. So today, I'm here to talk about what we've found makes for a good wheelchair and how we define the idea of a good wheelchair. First, a little bit about me. I graduated with my bachelor's in mechanical engineering from Clarkson University in upstate New York in 2016. During my time at Clarkson, I researched different material science applications of trabecular bone and supercapacitor electrode specimens. Obviously a pretty far cry from the rehabilitation engineering field where I wound up. In 2016, I came down to Atlanta and started my studies for my master's and my PhD at Georgia Tech. And in 2020, I graduated with the master's in mechanical engineering, as well as the PhD in bioengineering. During my time at Tech, I researched mechatronics, some biomedical devices, a lot of rehabilitation engineering and assistive technologies. And since 2020, I've been hired on as a postdoctoral researcher in the Rehabilitation Engineering and Applied Research Lab under Dr. Stephen Springle. Some of my work at the Rear Lab you may have seen before. Primarily, I focused on wheelchair testing using the anatomical model propulsion system, or the AMPS, robotic wheelchair tester. I also spent some time working with cushion testing to figure out pressure redistribution properties of wheelchair cushions and some vibration measurements. I've also worked more recently with some orphan assistive technologies, just some one-off projects that help improve the quality of life for wheelchair users or other folks with mobility and physical impairments. These include the pill dispenser and the hair management device that you see presented here, as well as an in-bed mobility device that I currently don't have a picture of, and a wheelchair tire cleaner or a wheelchair tire washer to get clay and mud and dirt out of the wheelchair tire treads. So you may have seen some of these floating around. I believe we've worked with some of you to design these in the capstone course with our engineering students. All right, without further ado, I'm going to get into the actual guts of the presentation. Most of this should be review for you all, but just bear with me. So first, the types of manual wheelchairs, or MWCs, that we're talking about, as defined by the Healthcare Common Procedure Coding System, or HCPCS, ranging from K1 being a standard chair that you'd see at a hospital or an airport. It's generally the simplest design for a wheelchair, typically folds up for storage. It's fairly hefty, normally made out of some sort of steel frame with a large seat to accommodate the widest range of people. This category is defined typically by its heavy frame, greater than 36 pounds. K2 is a standard hemi height, which means the backrest is shorter or adjustable. K3 is a lightweight chair. Really the only difference here, I mean, visually there isn't much of anything. The only difference is that the frame weight is between 34 to 36 pounds. A K4, or high strength lightweight, is 30 to 34 pounds for the frame weight, and it comes with this limited lifetime warranty for the frame. Finally, a K5, or an ultra lightweight chair, has less than 30 pounds for the frame weight. It has that limited lifetime warranty on the frame, and it also has this feature of being customizable. So you can, when you purchase the wheelchair, you can decide where you want the axle, the rear axle to be placed, what wheels you want for the casters and for the drive wheels, frame angles, footrest angles. All of these options are available for K5s. Just a little background on this. K1 through 3 is primarily intended for short-term use. This means, post-surgery recovery, so less than 3 months and less than 2 hours of use per day, versus the K4 and K5 chairs, which are intended primarily for self-propulsion using the push rims for long-term use. That means greater than 2 hours a day, greater than 3 months total of use. So a bit more of the numbers before we get into the fun stuff. So according to the US Census, in 2010, there were 3.6 million wheelchair users in the country. Now, this does include power and manual wheelchairs. Yet in 2014, that number had grown to about 3.5 million. And the current estimates are that we gain 2 million new wheelchair users per year. Now, this is, again, power and manual. So it's not just for manual wheelchairs. But for example, out of the 2017 data, 79,000 manual wheelchairs were prescribed to users. Out of this 79,000, 62% use the standard chair. 2% used the height adjustable standard chair. 24% used a lightweight chair. Now, these are all for short-term use. For full-time use, 5% were prescribed K4, high-strength lightweight, and only 1% used a K5 ultra lightweight, customizable frame. This is important because our problem overview is that wheelchairs are hard to propel. This shouldn't come as a surprise to any of you. And the way we know this, the way we put it into numbers, is typically with some form of efficiency. So in this case, gross mechanical efficiency, or GME. You can see that wheelchairs have the lowest GME out of other comparable modes of transportation. So wheelchairs ranging from standard to ultra lightweight have a GME of 3 to 7%, which is much less than the average person walking at a normal speed of maybe 1.2 meters per second at about 15% GME. And bicycling is by far the most efficient manual transportation at nearly 23% for the average user. Now I have to ask the question, why does it matter? Right? For wheelchair users, inefficiency means more frequent pushes, higher strain at the shoulders, the elbows, the wrist, higher risk of injury from repetitive strain. And any sort of injury or just using a chair in general can lead to lower community participation. So you've got all of these mental and physical health factors at play when you're talking about the inefficiencies of wheelchairs. And we know that better parts and configurations can improve performance. Yet only 1% of that population that were prescribed chairs in 2017 even had the option to configure their chair. And I'm talking, of course, about the ultra lightweight wheelchair users. So I'd like to do a little interaction, a little engagement with the audience here. Why are they hard to push? Becky, you can chime in here if you'd like. Do you have any ideas? What parts of the chair make it inefficient and hard to push? Shout out one or two things. Weight?
The weight.
The weight, okay. What else?
The material of the floor.
Okay, the surface you travel on, yep. Absolutely.
And then the wheels, different types of wheels may matter.
Yep. Yep. Anything else?
And the weight of the person.
Sure. Yeah. So, yeah, that's absolutely correct for the most part. Wheels are the primary interaction between the wheelchair and the surface you're propelling over. And wheels aren't always efficient at rolling. So depending on the tire type, whether it's a solid wheel or a pneumatic wheel that you can inflate, as well as what the wheel size is and how well the wheels are aligned with the direction you travel. You know, you don't want to propel a chair where the wheels are, facing inward like this. And the material, of course, if it deforms a lot, it's probably not going to roll very efficiently. The weight over each wheel. So this sort of bundles together the weight of the occupant, the position of the person in relation to the wheels and that rear wheel axle, as well as the weight of the system combined, so the person plus the frame. There's also biomechanics involved. So the user needs access to the wheels. If the wheels are too far back behind them, they can't even grab the wheels in the first place. And so there's this delicate balancing act of getting them into a stable position with the wheels far enough behind them so they don't tip over, as well as having them far enough that you're not sitting primarily on the casters. You're not putting weight over these tiny wheels that are hard to roll. So you need to consider this trade-off of stability versus maneuverability. And of course, as you mentioned, frame material, as well as the folding mechanism. If it's a folding frame, does it have a scissor folding mechanism in the bottom, or does it just snap into place? Do you have detent balls and poles that you need to snap together? So the big question is, how do we know all of these different things matter? Current wheelchair tests take many different forms. You can split them up primarily in two different ways, either system and component level, or with and without human subjects. So I've chosen to split them up at system level. So if we look at the wheelchair as a vehicle, we can test them with human subjects. We can instrument the chair to figure out how hard someone pushes in terms of wheel torque and wheel speed with either encoders or loggers, instrumented push frames. We can also look at how much energy the user is actually expending with metabolic cost. We can do mechanical tests for both system level and component level. So we can place a wheelchair loaded with some sort of wheelchair dummy on top of a drum tester, a dynamometer, just a roller or a treadmill, and see how efficiently it rolls. And we can just take the wheel off and put that wheel on the treadmill or roller and see how well individual components perform. One example of this is in the bottom right, this giant component test rig that measures rolling. So I want to flash back real quick to the problem statement. Again, manual wheelchairs are difficult to propel. The reason this is important is because more efficient chairs mean the user has to exert less energy, lower forces, and they're at a lower risk of injury with this more efficient vehicle. Yet, there's nothing currently existing to help us objectively compare different manual wheelchairs by performance. And that's what we're trying to change in my work and in general at the Rear Lab. So I want to take you through a thought exercise. Just picture, if you will, a world where cars are everywhere, but gas mileage doesn't exist. It's not advertised, it's never been thought of. And I'd go so far to say that car companies insist you don't want this. You don't want this performance metric to compare cars. Instead, you want to look at the weight of the car chassis, the material it's made out of, the weight capacity, how many people, how many tons of bricks can you fit in the back of the vehicle, and the warranty on the frame. And there's a heavy implication that all of these things affect cars' performance, but they have no evidence to actually prove these things. Right? Everyone with me here? It'd be weird, right? It'd be a lot more efficient just to have a gas mileage rating. But this is the world we live in. This is the current state of the wheelchair industry. There is no way to rate how good, say, a K3 or a K4 is versus a K5, whether you're traveling indoors or outdoors, over sidewalk, over carpet, there's nothing. And so this is how we measure performance. We've spent about the last 15 years putting together a test rig to measure wheelchair efficiency. This is the anatomical model propulsion system, or the AMPS. It's shaped more or less like a humanoid, made out of solid aluminum. And it's meant to resemble the size, weight distribution, overall shape of the average wheelchair occupant. I want to point out a few subsystems. They're largely unimportant to the presentation. I just think it's fun. So the head is a laptop. On that laptop, we run a software that controls the entire robot. It sends commands to the motor controller at the chest, that blue box, which then sends electricity to the motors that are grabbing the wheels. Now, In the abdomen area, we've got this data acquisition board that brings in signals from our wheel encoders, from our motor encoders, and from our current sensors to figure out how much torque and speed are occurring at the wheels. And on the right, you see a little detailed view of the motor and how we actually grip the wheelchair wheels. So the nice part about the amps is that it fully controls the occupant characteristics. So instead of using a human subject or many human subjects that all have different, loads and sizes and weight distributions, the amps has one that we can control very strictly. We can also control the propulsion of the system. So we can tell it to propel straight forward at 1 meter per second for 10 meters. What this gives us the power to do is to start generating a performance parameter. We call it propulsion cost. But essentially, if you drive straight forward 10 meters and you can rack up all of the energy that you spent propelling over those 10 meters, then you can get a ratio of energy per distance, very analogous to gas mileage. And it fully reflects how much energy someone would need to propel from point A to point B. All of our amps tests were originally based on the things we saw in everyday manual wheelchair usage. So Dr. Sonderblum from the lab measured daily activity of active full-time wheelchair users and found that on a daily basis, they travel between 1.4 to 1.6 kilometers over about 1 hour of cumulative use throughout the day. But individual bouts or spurts of mobility, every time they move, it would be short, so less than 30 seconds. It would occur very slow, so 0.4 to 0.6 meters per second. You can sort of get a reference of speed because a normal walking pace is about 1.4 meters per second. So very slow, with frequent stop, starts, and turns. So we tried to develop maneuvers based on these common parts of motion, whether it was straight with a fixed wheel turn where you grab one wheel and hold it and propel the other wheel, so you sort of turn around your left or right side, as well as a zero radius turn where you propel forward and backward at the same time on different wheels to spin in place. Here's a video of one of the more recent tests. I wanted to show off that we do propel in a straightforward line with the amps. It's not very fast, but it does reach around 0.8 to 1 meter per second. And it travels for a solid 18 seconds. So this is one amps trial. This is how we test all of the wheelchairs that I'll talk about for the rest of the presentation. And so now I want to just give you an overview of the studies that I'll go through. Our overall goal was to investigate the performance of different wheelchairs with different components and configurations, whether they're loading configurations or environmental configurations. I have 6 specific studies I'd like to talk about, time permitting. The first is testing the wheels themselves, so component level testing. The second is testing those same components with the amps at the wheelchair level. The third is using those results to try to improve as best we can a lightweight wheelchair. The fourth is to investigate frame mass and how much it matters on propulsion cost. Number 5 is assessing vibration dampening components. I'm sure you've seen and heard of a lot of those on the market. And the final study compares folding and rigid frames before and after about a year's worth of use. So I want to stop here real quick and make sure I want to address any questions you may have. We've also been going for about 20 minutes. So do you have any questions about the amps, about our setup, about the overview of what we're trying to do?
You mentioned problem statement in one of your previous slide, and in this slide, general, objective, and specific studies are all actions that you have been taking to solve that problem problem statement, right?
Right.
Okay.
Yeah. Well, wheelchairs are difficult to propel. So all of these studies are trying to identify key components that make wheelchairs better or worse, whether it's the wheels, whether it's the frame weight, whether it's the weight distribution. Yeah, that's exactly correct.
Okay, thank you.
All right. Okay, so I'll jump right into study one. This covers some component testing we did about, 3 or 4 years ago. We measured energy losses that occur at the wheel, and we wanted to compare different casters and drive wheels that are commonly sold for wheelchair users. The idea is that tires, being your main interface with the ground, are your primary source of energy loss. Tires lose energy both when they roll and when they scrub. So the general idea is that when you have a tire and you load that tire against the ground, it forms a flattened spot on the bottom of the tire that you rest on. This is the contact patch. The problem is when you roll, that contact patch sort of has to scurry along the perimeter of the wheel, right? So as the wheel rolls, that contact patch is constantly changing the spot on the tire that it exists, right? And the difficulty is that there's unequal energy. So it takes more energy to deform the tire than you get back when it springs back into position. This is known as hysteresis loss, and it's what generates this rolling resistance when you're just coasting down a hallway. It also exists when you're dry steering or scrubbing a caster or a drive wheel against the floor. The way we measure rolling resistance is using this coast down cart. Right now it's just a plywood platform that we load up with different bar weights to resemble the loading conditions of a wheelchair. And we can attach either drive wheels or casters to this thing to measure the rolling resistance of each type of component. We've tested, I believe this is 8 different casters shown in the plot on the right at different loads. So we configured this cart to put about 10, 15, or 20 kg over each of those 2 casters, just to see how they behave under different loading conditions. And we found that rolling resistance is basically proportional to the load on the cart or on the caster, right? And diameter has a pretty big effect. So a 3-inch diameter caster wheel is going to have a lot more rolling resistance in general than, say, a 6-inch caster wheel. Now, to measure scrub torque, it's a bit more complex. We've got this load frame in the back, and we've attached a giant aluminum structure to the front of it. Essentially, when we lift this, can you see my pointer? Yeah, okay. So when we lift this load arm in the back, this gray bar, we pull this up, and it pulls a cable around this pulley, and then it spins this spool. The spool is loaded by this big weight on the top, and we push this plate against the top of whatever component we're testing. Could be a caster, could be a drive wheel. And so we can again test the resistance of these wheels to scrub under different loads. So we again loaded each caster with 10, 15, and 20 kg and saw how the scrub resistance changed under each of those loads. And we noticed that sort of the exact opposite of rolling resistance, the larger casters actually have the most scrub, and the smallest ones have the lowest scrub. So this 6-inch pneumatic performed the worst out of the bunch, and the 3-inch caster actually had the lowest scrub. I can't click when I'm in this. Okay. So we tested this over a series of components. We chose a relatively representative cohort of components, things that are normally offered when you choose an ultra lightweight wheelchair. The default options or no cost options are typically this 5 by 1 inch solid caster shown in the orange box on the top, as well as this stock standard pneumatic tire on metal spoke wheels shown in the bottom row in orange. But you also have things like the wide soft roll caster, the wide but smaller soft roll caster, and pneumatic casters do exist. They're not necessarily common, but they do exist. And for drive wheels, you of course have the solid mag wheel, just a solid polyurethane wheel on a composite plastic hub. And you see very commonly these Spinergy wheels, which were supposed to be high performance spokes with a high pressure narrow tire. So we wanted to test them and see how they performed. These plots that I'm going to show you, I just want to briefly explain how they're set up. So the scrub torque is on the vertical, the y-axis, and the rolling resistance is on the x-axis. The ideal performance, of course, is as close to 0 on each axis as we can get. I chose this box fairly arbitrarily, but you get the point. So if I plot all of the data from our different casters, you can see some trends. I'll get my pointer back, laser pointer. So when we're testing on tile, the rolling resistance is fairly low for each of the components. If we test on carpet, the rolling resistance gets much higher. And this is exacerbated when it's a small caster. This is our 3-inch caster. It just gets blown out of the water for rolling resistance. It's so much harder to propel over carpet than any of the other tested components. But the scrub doesn't really change, and the scrub is of course related mostly to the size of the drive wheel. The smaller the better when you're trying to scrub or swivel. Again, we'll go back to these common components. So the in comparison to that 5-inch by 1-inch solid caster, this is how the other common components perform. The soft roll has a bit more rolling resistance, about 20% over tile, less so on carpet, only about 7%. And in scrub, it's considerably better, at least 47% less scrub. With the smaller diameter soft roll caster, rolling actually decreased. So it had 30% less rolling resistance on tile. And scrub, again, much better than the default. And for the pneumatic caster, surprisingly, it gained 54% more rolling resistance on tile. It's kind of an interesting result. And the scrub decreased compared to the default, but not by much, about 30%. Now, if I plot the data for the drive wheels, there are a few trends present. So the solid versus pneumatic wheels are the most prevalent discrepancy. If I group all the pneumatics in this green circle versus all the solids in the red circle, you can see it's night and day difference. Like pneumatics have lower rolling resistance, just in general. This, I will point out, this Primo Express is a fairly good solid tire. So that might be an outlier compared to most of the solids on the market. And I also need to point out that the solid mag, I find this very interesting. If I plot this dashed line down the center, the solid mag wheel performs worse on tile than any of the pneumatics do, even on carpet. And you know how bad it is to propel over carpet. So just an interesting thing to point out. Now, again, if I compare these two common components to our default standard pneumatic component, you can see clear differences. The solid mag wheel has a whopping 350% increase in rolling resistance over tile, and it doubles rolling resistance over carpet. For the Spinergies, surprisingly, for a $600 set of wheels, they're worse than a standard metal spoked set. 54% more rolling, 27% more rolling on carpet. So there's more than just our work in the world for these components, and I just want to cover it. I don't want to spend much time on it, but I think it needs to be pointed out. Toe, basically how aligned the wheels are with the direction of travel, is apparently very important to rolling resistance. So according to Ott and the team up at University of Pittsburgh, excuse me, about 2 degrees of toe can actually double the wheel's rolling resistance. just an incredible amount of rolling resistance just from a little bit of misalignment. You're talking a couple millimeters of misalignment at the very extent of the wheel. And a large percentage of the population of their subjects had at least half a degree of toe. Also, pneumatic inflation. I find it important to point out that inflation matters, but not as much as you think. If you lose 25% of your inflation, you're down to 75% of your recommended inflation, your rolling resistance goes up by maybe 4 to 10%. That's not bad. It takes about 2 or 3 weeks of daily use to reach that level of inflation. If you let it go a little bit longer, that's about a month or 5 weeks, and you reach 50% inflation, you might get more rolling resistance by about 12 or 18%. And if you lose 75% of the air in your tires, rolling resistance only increases by about 32%. Right? Not nearly as bad as you think. In terms of metabolic costs, so testing with actual humans, the differences were only significant when you reach 50% inflation, and that's when metabolic costs showed an increase by about 12%. So people were using 12% more energy when you lost 50% of the air in your tires. And if you lose 75% of the air, metabolic cost was only about 10% different in a different study. So just not as bad as you think. So some general takeaways. I spent a lot of time on this study because I think it's important. The things that make a difference, the surface you propel over, any surface that you dig into, whether it's carpet or grass, you have much greater losses both in scrub and in rolling. Tire type makes a difference, definitely. So solid versus pneumatic. And solid drive tires are just generally speaking much worse for rolling. But for wheel maintenance, pneumatics do need to be reinflated. But it turns out that inflation isn't the end-all be-all that we all thought it would be. And any sort of toe in or toe out means misalignment. It should be checked when you're looking at a patient or a client's chair, just to make sure, because that much rolling resistance can't be ignored. So I'd like to take a brief minute to just have a quick discussion. How would you see yourself using this data? Or would you see yourself using this data at all when you're helping someone pick out their first manual wheelchair? Or when you meet with current wheelchair users, how might you use this to inform them on better configurations? And to build off this, what other information can we add on to this data set that would be of use to you? So I figure I'll give them a couple minutes to talk.
Okay, are you trying to say that we should totally get rid of the solid tires and just use the pneumatic tires?
Yes, yes, I am.
Okay.
I know it's a bold stance, but they're going to hear it over and over throughout the presentation.
Are you sure that like the performance of solid wheels are not also affected by, you know, how much weight this person is, the weight distribution, and other factors? And are you sure
So
that
we'll
other
get into
factors
that in
don't
the very next study, because remember, this is all just at the component level. This is not at the system level. So yeah, it has 350% more rolling resistance, but it's hard to actually inform what that does to the wheelchair itself. So the next study will address that.
Okay, so this is just still study 1, right?
Yes.
You have 5 more studies to cover.
Yes, they go quicker.
Oh my God.
They go much quicker.
Okay.
And we're at 30 minutes right now, 35 maybe. And I have 2 hours. And I'm going to have my discussions in the middle in between studies. So hopefully I won't need to use quite so much time at the very end for a discussion, but we'll see. We'll see. All right, I'm going to jump into study 2 if you're okay with that. All right, so study 2 basically performs all of this testing. All of these components are used on the wheelchair. And we studied the manual wheelchair level performance. using the amps and this idea of propulsion cost. All right, so again, we use this cohort of one set of default components, this 5-inch solid caster and this 24 by 1 3/8 inch pneumatic, sort of medium pressure tire. We had 3 other casters we tested, this wide soft roll, this smaller but wider soft roll, and the pneumatic caster. We also tested the wheelchair performance with the solid mag and the Spinergy with a high pressure tire on it. We tested over 2 surfaces, tile and carpet, with 3 different weight distributions, so 60, 70, and 80% weight over the rear axle. This is a fairly representative selection of configurations. So I wanted to go through specific examples because I think this is more useful than the component level testing, just for clinical implications. This is sort of a cumbersome slide, so hopefully bear with me while I explain it. If anything doesn't add up, let me know at the end. But for the default spoked configuration with our default 5-inch casters, we had about 14.22 joules per meter for our propulsion cost with 60% weight distribution. So you have more weight over the casters. If we move some of that weight back towards the drive wheel axle, that cost goes down to about 12 joules per meter. So you see about a 20% difference there. For the Spinergy wheels, this high pressure, high performance wheel, the $600 set of wheels, the propulsion costs were about 17 joules per meter at 60% and about 15 for 80%, right? A 29%, 20 to 29% increase over our standard tires. And for the solid mags, the ones that had the worst rolling resistance, we saw about a 55 to a 99% increase in propulsion costs. So a far cry from that 354% increase in rolling resistance, right? But there's still a difference, and it is definitely significant. So using a little bit about our context of wheelchair use, right? We're assuming maybe 1.6 kilometers of daily travel. So say a user spends 90% of their time propelling straight forward over a hard surface like tile. They spend a lot of their day in the office or at home where they have hardwood or linoleum tile floors. This equates to about 20.5 kilojoules of energy over the course of the day for the spoked configuration, standard configuration, and about 31.7 kilojoules for a solid mag. That's a fairly large difference. I'd say, a 50% increase in energy. So this amount of energy actually equates to almost 800 meters that they could travel extra with that standard spoked wheel per day. Or if you want to turn it into a more like number of exercises thought, it's about 570 full bicep curls with a 2-liter bottle of water. Not an insignificant amount of energy. That's fairly considerable. So now let's look at weight distribution. So if you had these spoked wheels at 60% weight distribution, so you're sitting pretty far forward in the seat, and then you shifted backward, so your back was against the seat back, you had about 80% of your weight over the drive wheel axle, that's about a 3.2 kilojoule difference. So much less than the wheel swap, but still fairly considerable. That's about 270 extra meters of travel just by shifting your weight distribution backwards, getting less weight over those casters. That is about 160 lifts, that bicep curls of that 2-liter bottle. So still a lot of energy, but you get more by just switching from a spoked or from a solid mag to a spoked. So this is a very small subset of our data. We tried to condense it down into a general linear model that just kind of picked at the different variables, like the weight distribution, the surface, the drive wheel, and the caster. So in general, I know we just talked about how weight distribution has a large effect for one single wheel, but if you average over everything we tested, weight distribution kind of drops out, right? There's only about a 4% difference overall over all the wheels and all the casters on tile. And it only varies by about 9% on carpet. So generally speaking, it's important for one configuration, but the configuration matters more. The surfaces are obviously influential. Carpet's always going to be more demanding than tile. In this case, it was about 68% more demanding just overall to propel straight forward over carpet. And then casters make sort of a subtle difference here. All the casters were within about 8% of propulsion costs of the default configuration, whereas the drive tires made larger differences. Solid mag was worse by 23% over carpet, 54% over tile. Just again, generally speaking, averaging over all of the other configurations. So some takeaways for this study is we've tried to identify things to prioritize, those being the tires. The wheels and spokes don't necessarily matter. We firmly believe that the tires are what cause the majority of the differences, right? If you tested a pneumatic tire on those solid mag hubs, they would be fairly comparable to the pneumatic on metal spoke tires, right? So the tires make the difference. It's also nice to prioritize the context of use. So if you know the environment people are propelling over and how much time they're spending during the day driving straight forward or trying to turn, maybe they pace a lot in a small apartment and have to do a lot of turning on carpet. That's important to know. And you can pick out configurations that are very efficient for that type of motion. And then finally, you can prioritize this stability versus maneuverability. We talked about weight distribution. The more weight you shift backwards over that rear axle, the more tippy the chair is. That's fairly well known. But it also means the more maneuverable you are. So wheelchair users sort of have to find their own balance at some point and decide what's more important to them. So I think the main discussion points I want to talk about are which metrics stand out as being the most useful. Is propulsion cost understandable at face value? Or is that percent change more valuable? Do you get anywhere with that raw energy? Or does it have to really be broken out into that equivalent daily travel, that extra meters per day? Or the number of activities, the number of bicep curls with a 5-pound weight or a 2-liter bottle of water. So Becky, you can speak to this for a second. Which one did you find most useful, most explanatory?
I guess equivalent propulsion cost.
You thought the cost itself was sort of good because it's that gas mileage, right?
Yes, because all the other things are kind of customized because like people do different activities. They depending on their lifestyle, they may be on carpet more often and they may be on tile more on solid wood more often. Like all these different scenarios are, individual dependent, but propulsion cost is like a consistently the finding is consistent no matter where you travel or who you are.
Right. Oh, that's great. I don't get that feedback a lot. Most people find like that.
Like someone may ask you, so what do you want to, so carpet versus tile, you did all these different materials on the floor, but eventually as clinicians, how do we help the subject to make a decision? Because this is kind of a personal thing, and we don't really know how much this patient may not even know, okay, how much do I really travel on carpet? How much versus, other solid floor? This is hard to control and hard to tell. This is sort of like an individual report thing. And if
Right.
whether they report accurately or not is a question, right? So this is kind of hard to control and out of our control, you know.
Yeah, that's true too. I mean, it does come down to the user and individual preferences and what they want to get out of their wheelchair,
Yeah.
right? When do they want to be most efficient, right? Does it pain them to go on sidewalk? Then customize it for sidewalk, right? Those are things that you as clinicians can employ this data for with context, right? You have that context, or you can at least get that context from the user. Ask them, talk to them. These are things you already do. So they're things that we in the lab don't get access to, which is why I'm asking these questions. This is very eye-opening for me.
Mm.
So, okay, I'm gonna move to study 3. We can come back to this if any other questions come up. Thanks. All right, so study 3 was using our knowledge from the component testing and from that initial AMPS testing to customize a K4 or a high-strength lightweight chair. We wanted to improve performance in the general indoor environments where we expect the K4 to be used, so over tile and carpet, without changing what it means to be a K4. And so a K4 chair is really only prescribed when someone is capable of self-propulsion and needs a chair for longer than 2 hours a day or greater than 3 months of use. So this is not necessarily a post-surgery or recovering from a broken leg thing. This is someone has trouble walking and just doesn't need to use the chair full time, but needs a chair some of the time. So the context of use for this, not being a full-time user, means the person's going to use it for common surfaces, typically probably indoors when they can go slow and steady and putter around the house. And there's this low maintenance component implication for a K4. So everything comes with, every K4 I've seen on the market comes with a solid drive tire and large solid front casters. We wanted to impose some budget restrictions for this study. So K4s cost up to $600 online from online distributors. Some of them cost less. I think this one in particular that we used for the study cost about $400. So we didn't want the components to be a $600 set of spinner jigs, right? We wanted to keep the components very minimal cost, so less than $100 total. And we ultimately wanted to answer the question, can wheel selection help us improve a K4 possibly to the level of a K5, right? So our experimental design, we picked out 4 different configurations. The first configuration that I'll call configuration A had the default original equipment manufacturer OEM components. So these giant 8-inch casters at the front and solid mag tires at the back. Configuration B, we swapped out the front casters with these $42 per pair 6-inch casters. Configuration C, we put the 8-inch casters back on and instead swapped out the solid mags for this Primo Express, which for a pair of tires is about $48. Then configuration D, of course, we swapped out both and just had a completely new set of components. And I just want to reemphasize, we knew the performances over tile and carpet of both of these components from study 1. So we specifically selected the best ones we could to demonstrate how powerful it is to know these performances. And we found that the right components make a difference, absolutely. The upgraded configurations, B, C, and D, were all significantly more efficient. So on tile, the default, as the manufacturer intended configuration, had a propulsion cost of about 22.8 on tile and 28 on carpet. Right? If we switched all of the components for the new ones, we got that tile cost down by 41%, down to 13.5 joules per meter. And then for carpet, We got it down by, that is wrong. That is way wrong. That should be 23.13. Can you make a note of that, Becky? Slide 34, D prop cost. Okay, so with the energy that someone would save by switching from the default configuration to this new configuration, they could travel an extra 1.1 kilometers per day, right? Nearly double the distance that they travel throughout the day for the same amount of energy. And they could also do, or instead, they could do 750 full bicep curls with 2 liters of water. Again, completely significant amounts of energy that they're saving just by swapping these components. And so for our discussion, I just want to say components matter, right? The tires and the casters make all the difference in the world. But we do have some design trade-offs to talk about. Right, the larger casters that came default on the chair, those 8-inch solid casters, are much better at clearing obstacles, right? Even over a 6-inch caster. The larger diameter the tire, the easier it'll go over bumps, the easier it'll traverse cracks in the sidewalk, the pavement. And not all forks fit all casters. That was one of the limitations of this study, is that we couldn't put on a 5-inch caster, our default caster. We had to use something that was 6, 7, or 8 inches for this K4 chair. I'd also like to say that the pneumatic components, we didn't try it based on our own imposed limitations, right? We wanted to keep this no maintenance chair. But pneumatic components could easily surpass the Primo Express in terms of performance advantages, right? And I want to leave you with this thought that energy losses occur at each tire. You have 4 tires on these things. So if you're losing energy, it's important, right? Good tires are vitally important. Every push, every coast, every bout of mobility, you're losing energy. You might as well try to conserve as much energy as you can. So for discussion, I'd like to just walk through a few of these rather than discussing, first of all. I think it'll save some time. But my question to you is, how can you test the goodness of these wheels or of these full configurations in the clinic? And one of the thoughts we had was, just based on some observations, is a wheel drop test. So if you have, if we flash back to that component testing, tires lose energy because they deform and don't spring back and return all that energy. So it sort of makes sense that if a tire bounces, it'll return a lot more of that energy to you, both when it bounces and when it rolls, right? So this is a clever little animation put together by software. We'll address them later on, but look at how many times this common spoked metal wheel bounces. Now the soft wheel is specifically designed not to bounce, so that's what they're trying to prove here. But you get the idea of this procedure. Just loading a tire, dropping it, and seeing how high it bounces, seeing how many times it bounces, might give you an idea of the relative performance level. We also have coast down. We talked about the coast down cart, but there's no reason you can't perform a coast down with an actual wheelchair, with a wheelchair dummy or an actual person sitting on it. So this is me dropping a couple chairs down a ramp from the same height. So when the weight, the center of gravity was shifted further forward of the casters on the left panel, you see that it stops much earlier than the 80% configuration where the wheels, the weight is more over the back wheels. That's over tile. But the same test can be done over carpet or whatever surfaces you have available to you in the clinic or in the home, right? This is us dropping it over carpet. And again, there's not much of a difference because carpet is so hard to propel over in the first place, but there's still a noticeable difference just between these weight distributions. Imagine what it would look like if we had a solid mag versus a pneumatic tire. So we've also come up with different ways to measure deceleration or rolling resistance. This was a capstone group from last year that developed a smartphone application to record accelerations and basically work like a wheel encoder to figure out how many revolutions and what speed you're traveling at. And they use this, I don't know why it starts halfway through the video, but they use this to track the deceleration and rolling resistance of a few different configurations. And they found that it worked fairly well. But you get the same results just by looking at the distance that a chair travels when you coast down. Or, just the relative, as long as you control the relative speed you start at, distance is a great method of just comparing two chairs. So any questions on this study? I know I kind of breezed through the discussion. I think when I'm actually there, I'll get some more time to talk with them.
Did you, in this study, did you actually say, do you have the conclusion that weight distribution, it's the weight distribution that matters, not about how much weight that the person has that matters, right?
Right, so all of the configurations we tested in this study had the same weight and weight distribution.
Okay.
The only thing we changed was the tires.
Okay, but I'm wondering, like, solid tire versus pneumatic tires, first of all, they weigh differently. I believe solid tires weigh more, right?
They do, but that does not matter. We will get into that literally the next study.
Okay. And what is the most expensive component in the a manual wheelchair?
The most expensive ones, typically it's the frame, but honestly, you can find wheels that cost more than a full frame if you're talking pure financial cost. Casters are normally the cheapest, but not always.
Okay, because you mentioned that tire is vitally important, so I thought that tires are also very expensive. That's why they're important.
The tire themselves are normally cheap. Tires are about $50. The wheels are expensive. The frames are expensive. Does that answer your question?
Yes.
Okay, cool. All right, study 4. We're on the back half of the presentation now. So I want to address the elephant in the room. This is a common myth. I'd like to call it a myth, but there's a campaign going around saying that, a marketing campaign saying that frame mass is the most important thing when picking out a chair. Right? There's an argument that the reason the HCPCS codes, those K1 through K5, standard versus ultra lightweight, the reason those are important is because of the frame mass. So we want to address that. We want proof to either support or dispute that claim and see if frame mass actually matters at the levels that they're implied to matter. And see if these HCPCS codes have any merit regarding performance. And to do this, we wanted to compare the performances or the propulsion costs of one manual wheelchair loaded with an extra 0, 2, or 4 kg to the bottom of the frame. This takes some background explanation, some rationale. So in what ways might frame mass matter? The HCPCS K codes insist that 6 pounds or about 3 kg of frame weight are all that separate standard and ultra lightweight manual wheelchairs, right? That 36-pound or greater weight limit for standard and that less than 30 pounds weight for the ultra lightweight manual wheelchairs. So it's true, if we go back to the physics 101, F equals ma. Force equals the mass times the acceleration. So if you want to get the same acceleration from a wheelchair that has a greater mass, you have to put in a greater force, right? That totally makes sense. It adds up. It's scientifically accurate. That's true. When you transport a chair, whether you lift it up into a vehicle or you lift it up to store, place it into storage, or if you hop up or drop down steps or curbs, right? That's when mass can come in, weight can come in. You have to physically lift or control this descent of this thing. So weight might be important in these activities. There's also this constant reacceleration. So every time you push, you have to let go of the wheel and the chair coasts down slightly before you can push again and reaccelerate the system again. So between every single push, you've got deceleration and you need to reaccelerate the system. Again, F equals ma. To reaccelerate a heavier system, you need greater force. Okay, so all of these things shape up in favor of frame mass, right? But I want to add some context. We're talking about 1, 2, or 3 kg, right? When you look at just a frame, that might be 10 kg or 13 kilograms. 1 kg added to that frame, it's about 10% of the overall mass of the system, right? It looks huge. But as soon as I sit down on that frame, the system is now 100 kg, right? It's got me and the frame. And that 1 kg difference is now a measly 1%, right? It kind of pales in comparison. So proportionally, the forces should only go up by about 1%, right? I mean, that sort of makes sense, right? We're not talking 10 kg differences. We are talking 1 kg or 2 kg of difference, right? All right, so in previous studies in the literature, we did a brief literature review, seeing how human subjects respond to different frame masses. And some studies used frame mass as what we call an isolated variable. So they specifically added weights to the frame. So in the study by Sagawa, he added 1, 2, and 5 kg in discrete groups and found that under no circumstances did it change the cardiorespiratory function significantly. There were slight differences, but it wasn't significant enough statistically to show any differences. A few other studies that added 5 and 10 kg, right, 22 pounds to the frame, found that there were no impacts on the kinematics. So the push time, the cycle frequency, the push frequency, the forces and torques exerted on the wheels. And another study found that 10 kg had less of an effect on the wheel torques and wheel speeds than just changing from a pneumatic to a solid wheel. Right, so again, that solid tire comes back up to haunt us. There's also studies that examine system level mass changes. So when I say system level, I mean they actually change the entire frame. So these studies were comparing, say, a standard chair to an ultra lightweight chair, not just adding mass. And of course, in these studies, you've got different weight distributions that aren't controlled. You've got different tires and casters that aren't necessarily controlled. So these studies that did actually find differences, right, with a 9 kg heavier chair, 6% increase in push frame forces and torques on the wheel, right? You have to understand that the wheels were not necessarily controlled. The tires were not necessarily the same between these two chairs. So that difference cannot be all attributed to the 9 kg difference. And the same with the 9.1 kg chair. It was actually testing a sports chair, very lightweight, very efficient weight distribution over the drive wheels, to a standard chair. So about the farthest, the most disparate wheelchairs you can think of, found only about a 17% reduction in metabolic cost. So altogether, it doesn't appear that mass on its own is relevant. For this study, we used three different configurations. We used an unloaded chair with just the amps on it. Then we added 2 kg to the axle, roughly where the center of gravity was. So it didn't change the weight distribution much, it just changed the mass. Then we added 4 kg to the same spot. We tested using 2 different maneuvers. One was a straight maneuver, shown in this left video, where we just propelled in a straight line about 10 meters. We also used a slalom maneuver, which was kind of fun. So this one starts by going forward to align the casters, and then it alternates between a left arm push, a right arm push, a left, and a right. They're both at fairly low common indoor speeds, just to get a decent representation of both straight and turning movements. And we found that mass really didn't matter. It didn't make much of a difference. With the default frame, we had fairly low propulsion cost, 8.9 joules per meter. Adding 2 kg changed the propulsion cost by about 1%. Adding 4 kg changed it by about 4%. Right? Not much at all, considering changing the casters is more important. Changing weight distribution is more important than all of these. And in slalom, we saw even less differences. So both other configurations only changed by about less than 2%. So I want to go through this thought exercise again. Assuming 1.6 kilometers of daily travel with 90% in roughly straight motion and maybe 10% in this slalom sort of turning, frequent turning. Adding 2 kg gives you a whopping difference of about 100 joules. And that's the equivalent of maybe lifting 8 2-liter bottles or traveling, what, an extra 10 meters through the course of the day. So we're talking about an insignificant amount of energy difference between these configurations. In summary, these small changes, and I call them small, but it's 4 kg. It's roughly 10 pounds that we're adding to the frame. You would probably notice 10 pounds if you had to lift up these frames, but they don't matter to propulsion costs. They don't matter to overground performance. And there's more than just mass to consider, right? Mass distribution tends to be much more important. So if you have to add anything to the frame, don't place it on the footrest where it's going to put more load over the casters that are very inefficient. If you're going to put a backpack on the footrest, instead put it right behind you. Put it on the seat back, as long as the chair is still stable in this loading configuration. And again, I want to leave you with this takeaway of, if you obsess over this frame mass, where the changes don't really matter, you're missing the bigger picture. All of these bigger factors like tires and weight distribution, you just completely ignore them. So let's discuss, because in the clinic, you're constantly exposed to this idea that all of these companies, the Tylites of the world, come in and say, we have the lightest frames. And that's important. And we're the most efficient because we have the lightest frames. You have so much more exposure to that than I do. So tell me, have I missed anything?
Well, I think what you can encourage them to do is to start writing, a manual book, just like what you just said, that, okay, tell the users that for their type of wheelchair, they should put their bags in the back of the wheelchair instead of put on their casters on their feet. Start putting together a user guide with practical suggestions to the users, right? Because I don't think the clinicians ever tell the users that, hey, a couple of useful tips for you, do this and not do that, and do this and do that. They don't tell. I don't think they ever told them that.
No, I don't think so. I think they try, but they
don't know.
They're not given the right information, right? They are constantly exposed to these companies that just say, we have the lightest frames, they're the most efficient, by us. No companies are ever coming in saying, our wheels are better, use us. They're saying, our frames are lighter, use us, right? So you're exactly right. They're being exposed to the wrong information, and don't have a choice. They sort of have to regurgitate this information to the users because it's the only information they have. So if we can better inform the users, why wouldn't we?
Yeah. Okay. Can we take a short break, like a minute? I need to pee.
Okay.
Okay, I'm back.
All righty. I'm going to restart the clock, or not restart. I'm going to continue the clock. All right. Only 2 more studies to go over. We're getting there. Study 5. We wanted to examine these energy dissipating components. I think you'll recognize a few of them once I start passing them around. So I'm actually going to bring a box of components with me to start passing around the room and just tell them these are the components we tested. We wanted to examine if they actually did reduce the vibrations for the user, and if the user would then have to pay a penalty in propulsion cost. So if they're eating vibration, they're eating energy, they're absorbing energy from vibration, from just traveling over a surface, do they also absorb energy intended for propulsion? And of course, we wanted to look at the health effects because if you lower the propulsion costs, you lower the risk of repetitive strain injury. And if you lower the vibration, you might lower the risk of lower back pain, or at least the prevalence of lower back pain. So these are the components that we tested. There's quite a few of them, so I'll go through them one by one. On the left, on the far left, you see a normal caster fork. This is just a rigid aluminum caster fork. This is what we tested for 5 out of the 6 configurations. This was our default. For one of the configurations, we swapped out this pair of forks with a set of forks, frog legs forks, that had this wedge in it, this elastomeric wedge. So it's supposed to have this built-in suspension. So when you hit any obstacles, it's supposed to deform this wedge and then spring back into place. Very cool design. We tested a set of course, the default spoke pneumatic wheels we use in every study. This is what we used for the bulk of all of our tests. We had a set of mountain wheels. So these are wider, 2-inch, very aggressively treaded tires that are meant for outdoor use. So they'd be good for like climbing a mountain. We have 2 sets of wheels with built-in suspension. So one of them down here is called the loop wheels, and it's got a set of leaf springs. It's got 3 different leaf springs that are sort of S-shaped that connect the hub to the rim. And we had soft wheels, which have 3 pistons or shocks that connect the hub to the rim. So they're meant for different things. One is supposed to just completely absorb energy and be rigid when you're not hitting things. The other one's supposed to deform and absorb energy when you're hitting things hard, and then return that energy to you because it's a spring. Then the 2 casters we tested were, of course, the 5x1 solid standard default casters that we always test, and a set of soft roll casters, those wider, more compliant, softer material casters. So I'd like to take a second and discuss, because I like doing that, which components that I've just handed out do you expect to help with vibration? So think about driving over a cobblestone road in Italy. Which ones do you expect to help with impacts or shocks? So going over a door threshold or hitting a pebble on the road, a single pebble. What about heavy shocks like curb drop or bumping into something hard at high speeds? And which ones do you think will help or hinder the propulsion cost? So do you have any thoughts on these? I know it's hard because you don't have the components, but any impressions are good.
I'm guessing this soft roll. I don't know the third one, the bottom one that has
This one?
three. No, the
This one.
left. Yes.
This is
What
the
is it
loop
called?
wheel.
Okay. Either the loop wheel or the soft roll caster.
These two.
Uh-huh.
Which one? What do you think they'll do?
Reduce the amount of bounce. Oh, yeah.
Okay.
It cancels out the bouncing process. Vibration. Cancels out the vibration.
Okay. What about the rest of them? Do you think this will do anything?
Inside the ring, it looks interesting. These three little things.
Yeah, they're shocks.
I just don't know what they do,
So they're dampers, basically. They're
Okay,
supposed to
that
compress.
should help a lot.
Right. They're supposed to be rigid when you're just driving over a flat surface, and they're supposed to compress if you hit something really hard.
Okay, then this would help. Yeah.
Okay. All right. So I don't want to spend too much time on this. I think once everyone gets their hands on some of these components, that's enough for me. That's, they'll see them, know what we're talking about. So we attached a few accelerometers to a wheelchair, just a rigid framed wheelchair. We attached three different ones. One on the seat where the user would actually experience the most of the vibrations. One underneath the seat, because it's a rigid frame, we had this nice bar that went across underneath the seat. So we attached one there pretty close to the drive wheels to see how much vibration would get through the drive wheels, through the axle, transmitted all the way up to the frame. And we put one on the caster, basically right above the caster fork, to see how much raw vibration we were getting just from the casters, because they're really the first things to hit any obstacles, right? And because they're such a small diameter wheel, we figured they would see the most vibration. But today, I'm just going to focus on the seat. I think that's the most relevant. It accurately reflects how much vibration would go straight up into the user's spine, basically. So I think that's the most important. We tested over 4 different surfaces. So the brick, just interior decorative brick. The squares are about 6 inches by 6 inches with a small relief joint in between each one. So you get this nice repetitive impact every time you go over a square. We tested on grates, which they're awful. I mean, they feel terrible. They sound terrible when you roll over them. I don't even like walking over them. We tested over a generic strip of sidewalk, sort of large pavers. So you get the sporadic relief joint in between the sidewalk squares, but otherwise it's a fairly flat but rough surface. And then we tested over the generic tile, the linoleum tile, for a very smooth, flat surface. And our general results showed that the vibration wasn't really all that harmful. Kind of a shock to all of us. But because of the context, right? Users propel very slowly, less than 1 meter per second on average, with short bursts of mobility and less than an hour of cumulative daily use of the chair. And so as we tested over these different surfaces, we saw that tile, we had this acceleration value of 0.182 meters per second squared, right? About half the vibration of the rest of it, right? Brick, sidewalk, and grates were all around 0.35 meters per second squared. Now, to put that in context, we checked what the ISO International Standards Organization recommended for daily vibration exposure limits. And we wanted to compare it to this warning zone, right? If you have 0.5 meters per second squared of exposure for a cumulative 8 hours a day, they say maybe you should reconsider your life choices, right? You should probably find a job that treats your body a little nicer. And then if you hit 1.15 meters per second squared for a duration of 8 hours, that's when they say, okay, you're definitely at risk of health effects. You know, this is where lower back pain definitely starts to come in. This is where neck pain and, you know, neural fatigue comes in, neuromuscular fatigue starts coming into play. And so these values down here reflect how much time of daily travel it would need over each one of these surfaces to reach these different levels. Right? Over tile, you would never reach this warning zone. It would take over 24 hours of continuous motion to reach this warning zone limit. Over brick, sidewalk, and grates, it's a little bit different. It takes about 14, almost 15 hours on average of continuous daily travel to reach what's considered this warning zone. So we can pretty clearly say if someone's only propelling the chair for about 1 hour, they're never going to reach this warning zone, right? Also, riding MARTA, right? A single trip on the MARTA exposes you to anywhere from 0.4 to 0.7 meters per second of this vibration, right? At least double what you'd be exposed to traveling over tile, and sometimes twice what you'd be exposed to over brick, sidewalk, or grates. So if someone comes in and says, I need to reduce my vibration because it's damaging my health, I mean, based on the data, you would think that riding on the MARTA would be excruciatingly painful. And riding on high-speed rail, so this is from a study in Egypt for a high-speed rail in between Egyptian cities, the vibrations were even higher. So they were about 1.2 to 1.8 meters per second squared. And so these actually do put you at risk of health effects at these levels, but wheelchair use is nowhere close to those. It's now the general overview, comparing propulsion costs in this block of data and seat vibration to this block. We see that for the casters, everything's fairly close to our default configuration. So nothing's harmful, nothing's out of the ordinary. In fact, these yellow boxes are actually statistically equivalent to the default configuration. All right, so soft roll and frog leg forks didn't change propulsion cost at all compared to the default. The drive wheels, on the other hand, you see that the loop wheels and the soft wheels, right? The loop wheels here with the 3 springs and the soft wheels with the shocks or the dampers, they increase propulsion cost by over 10%, right? 12 to 17%. Now let's take a look at the vibration exposure. Only one component, these soft roll casters, reduced vibrations at the seat. The frog leg forks, unfortunately, increased the vibration at the seat for every single surface. And then the loop wheel, right, this springy one, actually increased the vibration as well. So it did nothing beneficial for the user in these particular circumstances. So in a little bit cleaner of a format, let's go through the results. These frog leg suspension forks, the springy forks, increased the vibration over all surfaces. The soft rolls, on the other hand, decreased vibration on the more aggressive surfaces. Mountain wheels didn't really do anything, which is good because it means you don't really pay a penalty in propulsion cost, and it doesn't change your vibration. So if you want something that gives you a wider base of support and more traction, mountain wheels are the way to go. The loop wheels, right? The springy ones increase vibration and propulsion cost, and the soft wheels increase the propulsion cost. So now I want to play a little game. So Becky, based on these results, how much do you think these things cost?
You mean money-wise?
Money-wise, yes. So let's start with the suspension forks. Right, that springy set of suspension forks I showed you. How much do you think they cost?
$100 or $200.
Oh, very, very close. Yeah, $300.
Oh,
So in this case, they didn't improve anything, but they cost $300. Right. What about the soft roll casters? What do you think they cost? I mentioned that soft casters in general were fairly cheap, right?
yeah, they're around 100 or under $100.
150. You're right on. What about a set of mountain wheels? They're almost like
They
set
might
of-
be expensive. Like $300.
You're right on. Wow, holy crap. Have you seen this slide before?
No, but as your girlfriend for all these years, you trained my instinct.
Oh, I see. Okay, what about loop wheels? Right, that one with the springs, the one that looked really cool with the 3 S shapes.
$300? Wait, 2,400.
$2,400 for them to do active harm to your propulsion cost and your vibration exposure. $2,400. Now you can
Wait.
find them pre-owned for about $1,500, but this is from an online distributor, $2,400 to buy a pair of these. That doesn't include the tire. It's just the
And
wheel.
so that wheelchair will be super expensive.
Yeah, super expensive, and it doesn't help your vibration or propulsion cost. Right? What about the soft wheels? Let's just round out this slide. What do you think they cost? That's the one with the shocks on the inside, the 3 rectangular shocks.
$300?
17. So these specialty wheels cost an arm and a leg, and they don't help with vibration. All right. So let's go into takeaways, because I don't want to give you the wrong idea. Vibrations were not harmful for any of these situations. So even if you use the frog legs forks, the vibration is still not harmful. It's just less good than default for the most part. So I'm going to ask the clinicians, do you have patients or clients that use these components? Do you see people with these things on? And why do you think they have them on? Right? Because there are legitimate reasons. If you spend a lot of the day being active and dropping off curbs, dropping down a staircase, some people can do that. Some active users have the capability to do those things. Right? In those specific cases, things like the frog legs forks and the soft wheels can do a lot of good, right? Because they are great at impact. But you have to understand that you pay a penalty every time you push. Your energetic cost goes way up by using these things for a benefit of dropping off the curb maybe 3 times a day at most. And you pay a penalty in some cases with the vibration. So just keep those things in mind when you see these components, that they're not always good. You can't just take the manufacturer's word that they're the best thing since sliced bread. Right. All right, I want to finish out strong. So here is study 6. What we wanted to do with this study is compare folding and rigid frames. That's sort of the last configuration option decision someone has to make, or rather, it's the first decision someone has to make when they're picking out an ultra lightweight wheelchair. They need to know, do I want it to be folding so I can put it, fold it up and put it away? Or do I want it to be rigid? And it folds up a different way, but it stays the same footprint and is generally seen as a more stable chair. And then we wanted to test how they behaved before and after about a year's worth of use. These are the chairs we tested and the surfaces we tested over. We chose 2 rigid chairs, a Quickie 5R and a Kushal K series. That's part of Invacare's new line. And we tested 4 folding chairs, a Key Catalyst 5, a Carmen Flex, a Drive Cougar, and a Kushal Champion. We tested each of these chairs brand new out of the box over this flat concrete, which is awful smooth. It's used as a forklift pathway, so it has to be very smooth, but it's got some texture to it. It's got a very rugged surface that's a little bit more textured than a linoleum tile surface. We also tested over carpet, but differences over carpet aren't so clearly visible, so I'm going to exclude those from the presentation. And we found that for brand new chairs, given the same wheels and tires, same weight distribution, same basic loading, the rigid chairs have about 8% of a performance advantage. They're better by 8%. So again, we only tested 2 rigid chairs and 4 folding chairs. So this may not be generalizable to all rigid and all folding chairs on the market, but it's pretty significant. We then tested over a circle track or a carousel tester. We wanted to put these chairs through hell and just beat the ever-loving hell out of them. And so we ran all of these chairs around this track for 71 hours, traveling at 1 meter per second. We had a few obstacles on the track. So we have this diamond plate that you see in the video. It's just about a ½ inch tall, and it's got some protrusions. So it's meant to be very bumpy and very aggressive. We also had a double-sided 3-inch ramp that they would roll up and then drop down, and then a door threshold about 5 inches wide and about a ¼ inch tall for them to bump up and over. So we drove these things around the track for 71 hours. And then since we wanted to distribute these cornering forces equally and get the turning tire worn down as much as the inner tire, we flipped the directions and drove them 71 hours in the opposite direction too, for a total of 142 hours of simulated use. This represents 511 kilometers of travel, or roughly 1 year's worth of use. And when I say I beat up the chairs, I mean we beat up the chairs. There were clear signs that we were basically destroying these tires. The friction alone scrubbed off about 2 or 3 millimeters of the tread on the drive wheels. And it looked like most of that tread just built right up on the casters. So you can see here, this used to have sort of a bump out, another knob here that's completely worn off. And then all of the material that was scraped off of this looked to have built up around the caster. So it's just sort of bizarre, but you could clearly see that we were beating up the chairs. We also had a few broken spokes on the wheels and some flat tires, but we repaired those and replaced them before we did any major testing. Oh, and we noticed that between the new and the used conditions, the propulsion costs actually went down. So the performance improved after breaking in the chairs. It wasn't a significant improvement, just sort of an anecdotal one. So we saw a 3% increase, 3% performance boost for folding and about a 10% performance boost in the rigid chairs. But it wasn't enough to be statistically significant. And not all the chairs followed the same trend. So one of the foldings actually got worse with wear, as you would kind of expect. But in the new and the worn conditions, folding chairs are worse. About 8% brand new out of the box, and about 14% when they're worn down after a year's worth of use. So it does seem that the rigid chairs have an advantage and just generally wear better, but there's nothing to suggest the folding frames really got worse. So again, rigid chairs, slightly more efficient, possibly due to the fact that they are rigid and all of your energy goes into propelling the chair rather than deforming and flexing the frame. But this performance difference varies between frame to frame and between manufacturers, makes, models. Every chair had pretty high performance overall. Nothing was concerning. Nothing stood out as being a terrible chair. And like I said, there's no indication that a year's worth of use was detrimental and harmed the performance drastically. In fact, wearing in the bearings and the wheels and the locking, the folding mechanisms might actually help with the performance overall, anecdotally. So here's an overview of all the studies that we went through today. We've talked about these easy to deploy coast down and scrub tests for the components and how they correlate pretty highly with the wheelchair level amps tests. We found that tires make a large difference, of course. I think I beat that dead horse pretty well today. Tire type, inflation, alignment, toe in, toe out, they all make a difference. They all should be considered when you're seeing patients or clients. You should also keep in mind that frame mass doesn't appear to be significant, right? At least not at the level of 6 pounds. So the differences between a standard and an ultra lightweight chair, yes, a standard will roll to a stop much faster than an ultra lightweight chair, but it's not because of the mass of the frame. It's because of the solid mag tires. It's because of those giant, poorly made casters at the front of a standard chair. We found that vibrations aren't very harmful, so there's not much to be worried about except for comfort levels. But then again, some components don't really help the vibrations. Frog-legged forks, a very popular component upgrade option, didn't help vibrations at all. They might help shocks. They might help impacts if you go over door thresholds on a daily basis, but they don't help vibrations. And some even make it harder to propel the chair. And finally, we talked about how rigid frames are, generally speaking, about 8 to 15% more efficient. And that 1 year's worth of general wear and tear did not degrade the chair's performance at all. I'd like to acknowledge my funding sources. So we got a NIDLR grant to support all of these studies. We also got internal funding through the Rear Lab and through the School of Industrial Design from Georgia Tech. And I'd like to thank the members of the Rear Lab, the leadership, Dr. Spriggle, Dr. Sonnenblum, as well as our research engineer, Yogesh, who's helped drastically with most of these studies, as well as my advisory committee. One of you is here today. Thank you, Dr. Maurer, and thank you to Rita Stanley and Jody Dyer, who have helped us decide on the studies we'd like to perform and how to best address the questions we have about wheelchair use. I've got my references listed here. I can make these available to you if anything caught your eye. And now let's talk. I've left my contact info up here in case you'd like to reach out after the talk, but I'm happy to address any questions, comments, discussion points you may have today. And I can stay as long as you're free. I know we only had 2 hours blocked out, but I don't have anything planned this afternoon, so I can stick around if you want to talk further. Thank you.
I don't think you need to do any major changes or anything. I think you're totally ready. You just need to have a good sleep, be energetic, and relax when you walk in tomorrow, and that's it. Okay, I think you do still. Are you